Today in class we're going to be talking about exponential functions versus power functions. An exponential function in its general form we've established as being yabx, or y equals ab to the x. If you notice with the yabx function, the variable is an exponent. So your variable is the power in this case. Now when we're talking about a power function, instead of the variable being in the power, the variable is your base, and now the power is going to be a number. N is just going to be any number. Now when we solve these two functions, we need to solve them in different ways. There are ways we can solve both of them, but it does vary by the problem. If you take a look here at example A, we have several different problems for you to try. This first problem is going to be an example of a power function because the power is a number. Number 2 is an example of an exponential because the power is a variable. The next one is an exponential. Again, the variable is the exponent. Number 4 is a power function. The exponent is a power. If we look at 5, 6, 7, and 8, 5 is going to be a power. The exponent is 3. 6, it is going to be an exponential. The power has a variable in it. 7 is an exponential. The power has a variable. And 8 is a power function with the power being 4. In order to solve problems that have a variable as the exponent, you're going to need to be able to write the numbers with different bases. Sometimes there will be more than one way to write the base. For example, 36 could be rewritten as 6 to the power of 2. 81 is the same thing as 9 squared. 81 also is able to be rewritten with a base of 3, or 3 to the power of 4. 32 could be rewritten as 2 to the power of 5. 16 can be rewritten as 4 to the power of 2, or 2 to the power of 4. Now be careful, these are not just inverted. 4 times 4 is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. The last one here, 125, is 5 to the power of 3. Being able to recognize these different congruencies is going to help you to be able to solve exponential problems. Let's take a look at an example of this. If I want to solve this for x, I don't have an algebraic way to do that yet. However, if I can make the bases become the same, that means that the exponents will also have to be the same. We'll be combining our exponent rules along with the concept of rewriting the bases. For example, 4 to the power of x could be rewritten as 2 to the power of 2, and I still have that variable x outside of it. 8 can be rewritten as 2 to the power of 3. 2 to the power of 2 raised to the x using our power property ends up being 2 to the power of 2x. Now that I have it written like this, notice that our bases are the same, which means our exponents will have to be the same. That means that I can say 2x equals 3, and solving this will tell me that x must be 1.5, or 3/2. If I were to plug 1.5 in for x and use my calculator, it would equal 8. Let's give one more problem a try, and then I'll leave the rest of the notes for you to do on your own. We just did this one, but the steps to do these problems are going to be isolate the base, or exponent, find a common base, get rid of the bases, and set the exponents equal to each other, and then solve. Let's try B. Now in this case, 3 to the 3x equals 27. I want to try to write 27 with a base of 3. Well, I know that 3 to the power of 3 equals 27. By writing it in this form, I've now determined that I have a common base, and therefore I can set the exponents equal to each other. So 3x equals 3. If I divide by 3 on both sides, x must equal 1. Letter C is just a slightly different problem here, but we're going to still use the steps that I have listed on the right-hand side. In this case, I don't want to get a common base yet because I have this additional number out front. Let's go ahead and divide both sides by the 2 to eliminate that. This now gives me 5 to the x minus 6 equals 25. At this point, I need to somehow work with that exponent, and I can't do it with the way it's written, so I need to think about how can I write 25 so that it has a base of 5. 5 to the x minus 6 is equal to 5 to the second. We've now successfully gotten that common base of 5, so we can set those exponents equal to each other. In this case, we get x minus 6 equals 2. Adding 6 to both sides allows us to get an answer of x equals 8. If I plug 8 in for x and I do this math, it should equal 50. Be cautious. Sometimes you will have to write both sides as we did in the initial example. Sometimes you'll have to get rid of the additional numbers. Each problem is unique and it's important to follow those steps, although some steps may be skipped depending on the problem. I hope this video helps.